I'm in Denver. Recording
All
in
right.
progress. Okay, let her rip. Greetings to all of you from Denver, Colorado, to all of you Ohioans. Tonight, we are going to be talking about commercial multifamily boiler retrofits. It's a very hot market. Most of these buildings were developed by HUD in the 70s. This particular sample building that we'll be going through was conceived and built in 1970, and it was all hydronic throughout. I believe that the engineers that did the heat loss calculation on this thing looked at the loss calculations and decided that there was no way that was enough heat, and they doubled it. And
Oh,
basically, it had wall-to-wall baseboard all the way around the interior of the building, and the building had been through numerous retrofits, primarily due to residential complaints, people complaining that it was too hot. Pumps were too big and were causing zone valves to bypass. So they got heat whether they wanted it or needed it. And they eventually went through and installed some Danfoss non-electric thermostatic radiator control valves in an effort to be able to control the flow, but they didn't really do anything with the pumps. So they caused problems with the needle and seat assemblies on the zone control valves, the non-electric valves, and caused erosion there to the point where they ended up eventually getting back into the same problem again. But in any case, they called us up and asked us to come out and take a look at the building and review it for the potential of being able to replace the hydronic heat sources within the mechanical room itself. The baseboard, they weren't really too worried about, neither were we, because it was wall to wall. There was plenty of baseboard in there. So we started out. Basically, this is the exterior of the building. If memory serves me correctly, it was 13 stories tall. It is a HUD subsidized building, which any of those of you that have had experience in this market know that the people that live in these buildings that are subsidized have a tendency to complain at the drop of a hat if anything is wrong. And the
Mark,
poor folks, yes,
you gotta change your slide.
it
You go
didn't
to slide,
slide.
still on slide one. You gotta go to slide two. Gonna
Hmm,
lock up on us.
it did. Hang on.
Done this before?
Yeah, we had a set half an hour ago. We're waiting for you.
Oh, I see. Sorry. Pay attention. She made it. I review the bid and see what it's like that.
Is it still on the first slide, Tom?
Yes,
Yeah.
it is, Mark.
Huh, I don't know what changed. Let me stop sharing. Can you see the second slide now?
No, it's you.
You just see me.
See you loud and good. Not the door.
We dropped the PowerPoint.
Apologies to the students here until we get this technical diffugely figured out. Let me go back to Zoom.
Tyflugery? A kerfuffle. Kerfuffle, I know
Diffugalty.
now, but I don't think I've ever heard. No, that's a new one. That's a new one. It's fresh. It's fresh. Yeah, that's right. He's the legend.
There you go.
Yeah.
Okay, well, I can see.
We're on slide two right now.
Okay, how about now? Three?
Three.
Yep, we're on slide
All right,
three.
back on track. Let's go back to two. So this is the exterior north end of the building, north side of the building. So obviously the south side is going to have the same basic square footage area, except that it's going to be seeing a lot of solar gain. And solar gain has a tendency to cause free gains within the space itself, which causes these non-electric thermostatic radiator valves and even regular thermostats to shut down. And in my personal experience here in Colorado, we hit design condition for less than 2% of the time, which means that the heating system is basically oversized for 98% of the time. And the worst thing that you can do to a heating system is to short cycle it. This was an exterior view from the south side. And by the way, Google Earth Pro can be your friend. Basically, we used Google Earth Pro and got ourselves the ability to be able to actually measure the dimensions of the building and multiplied that times the number of floors that we had and took a look at the sizing of the physical plant and basically divided the net output by the square foot of conditioned building to see how close they were. Were they in the ballpark? Were they out in left field? Where exactly were they in the sizing of their boilers? So basically, you could use Google Earth Pro to physically measure the dimensions of the footprint of the building itself and then take a look at the physical plant. What's driving it? This probably looks familiar to you guys. These are Ajax boilers. It's a water tube style of boiler, but you can tell by looking at the gas train down here that it's basically a 1/3, 3/3 type of operation. So when it's all the way on, all 3/3 are on. But when it's on low burn, the middle burner is on. And essentially what happens is you end up with a lot of dilution air that's going through the combustion chamber and it's causing your thermal efficiency numbers to basically go upside down. These boilers probably run about 40% efficient, thermally efficient when they are running on the low burner. Theoretically, you wouldn't think that that would make any sense because you're only putting in 1/3 of the energy, but you have no way of being able to control the primary air that's being drawn into the combustion chamber. So those tubes that don't have a fire under them become a radiator and they lose heat basically into the flue pipe, 13-story tall building. Don't know if you can see it here or not, but right over here is the control, the weighted controls for the barometric dampers for this venting system. There was probably 5 pounds worth of weights that were on that damper. So essentially the damper was closed completely. It was not alleviating the excess negative pressure that's being caused by the chimney. So it was drawing a significant amount of air through the bottom of the combustion chamber up through the combustion process. Both of these boilers, by the way, we found them were in the on enabled position. They were all both running on their low flame pretty much constantly. Domestic hot water originally was supplied by these boilers, but they had separated the systems and put in high efficiency condensing water heaters, which were failing. And a part of our original scope was not to include the water heaters because I felt they had just put those in less than 10 years and they were supposedly a 20-year life expectancy appliance. So we did not initially address the domestic hot water heating issue until we got on site. And we'll talk about that a little bit more as we get into it. But in any case, we had to maintain space heat supply while we were in the process of actually replacing this heating system. We couldn't shut it completely off because we did the startup of the system. I think it was in the spring. There was still snow on the ground outside. So basically, you got to run the numbers first. What do you need? All right. So we've got 4 million BTUs an hour on each one of those Ajax boilers. And we had two of them. So we had a total of 8 million BTUs per hour input. And that's at sea level. Here in Denver, we're a mile high. Probably have heard that on football games. So basically, we had to derate for altitude at a rate of 4% per 1,000 foot. So 4 times 5 is 20%. Right. So basically, the math is that you've got 8 million BTUs times 0.64, which would equal 5.12 million BTUs per hour net out. Now, how did we get to that 0.64? The boilers are 80% efficient. The altitudinal duration was 20%. The inverse of 20 is 80. So 0.8 times 0.8 equals 0.64. So the 8 million gross input times 0.64, which is the combined altitude and combustion efficiency net output, equals 5.12 million BTUs per hour net out. Does that make sense to everybody?
Is that the actual numbers for the load, or was they had 4 million boilers in there?
That's what they had in there. That was their driving force. So basically, they had a net output of 5,120,000 BTUs of heat. All right. The building dimensions of conditioned space worked out to be 29 BTUs per square foot per hour, which is really quite reasonable. 30 BTUs per square foot per hour is an industry standard that has been used for standard efficiency buildings for quite some time. You get into some of the older buildings that are strictly brick, where the brick wall has the same R value as the windows, your loads may jump to as much as 50 BTUs per square foot per hour, but 30 BTUs per square foot per hour for a building that was built in the 70s is a very reasonable number. That's something that I'm comfortable working with. I wouldn't throw a red flag and say, whoa, 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 we need to do a full heat loss calculation on this. But that's a nice thing about Google Earth Pro is you can also measure the exterior dimensions on the vertical elevations and figure out how many square feet of glass you've got. You know what the R value is. You know that the temperature differential is going to be for Denver, 0 degrees is a design outdoor air temperature. So if you got a 70-degree delta T between the inside temperature and the outside temperature, and if need be, you can do a full-blown load calculation on it. It's what we call a skin loss calculation. But coming in at 30 BTUs per square foot per hour, I had no problem with that whatsoever. So it wasn't necessary for us to go in and do a full load calculation. So we have to do what's called an EDR study, which is the equivalent developed radiation. This study, basically, you go in and measure the baseboard and find out what you've got. And then you assume a value based on the manufacturer's information of what its net output is. So we had basically 372 linear feet of exterior wall. And as I'd mentioned earlier, the baseboard was on every exterior wall. And so we had 372 linear feet of wall times 13 floors is 4,836 feet of baseboard. All right, so we take that 4,836 and multiply that times 500, which would be the BTU per hour output per linear foot. And we come up with a net demand of 2,418,000 BTUs of output capacity. Bear in mind, this is a government project. It was subsidized by HUD. They paid engineers to design this system, and originally it was doing domestic hot water. And domestic hot water, in a lot of cases on an hourly basis, will exceed what the space heating demands are. So it's not uncommon for them to grossly oversize the size of the boiler just based on the fact that it's going to be doing domestic hot water. And if the system has changed, which it had in this case, the domestic hot water had actually been eliminated and had been set aside by a separate standalone system, then basically we were looking at a demand for space heating of 2,418,000 BTUs per hour, not the, what was it?
5.1.
Yeah, 5.1 million BTUs per hour. So it was basically way oversized. So if we take the demand, 2,418,000, and divide it by the net output capacity on site, which was those 8 million BTUs per hour, which netted out at 5,120,000, then we end up with 47% of available capacity. And basically that tells us that the boilers were about twice as large as they really needed to be. And as we found the system, boilers were being cycled all the time, and they were all operating on low burn. And speaking to the chief engineer, I said, have you ever seen these boilers on high burn? And he goes, when it gets down below zero outside, they will fire, go to high burn for a short period of time, and then shut off, which is even worse yet. That's short cycling to the max. It just kind of enhances the draft action of the air that's being drawn up through the boilers. And the combustion air requirements to the outside on this thing were ridiculous. At the time that the building was built, it was basically a whole exterior wall that was louvered and screened, and that was their combustion air. So basically, you're keeping a hot boiler with a hot stack with a lot of negative pressure. It was probably drawing about a ½ inch of water column pressure at the breaching of the boilers themselves with barometric dampers that were overweighted. Those barometric dampers, for those of you that don't know, are supposed to be adjusted to maintain 2/100ths of an inch of negative pressure at the breaching, which means that in a lot of cases they're going to be standing wide open. But when an unqualified technician looks at them, he goes, "Oh, that's where carbon monoxide leaks come from." No, it's not. That's where the air is going in.
Yeah.
We did, yeah, they throw weight on them to close them so that it doesn't leak any carbon monoxide into the boiler room. And not uncommon at all. So Basically, this is a grossly oversized system that was being inoperated very improperly, with a lot of excess air being drawn through the combustion process, running on low burn, which compounds the problem even more. And essentially, they were wasting a lot of energy.
It was
And
designed to use as much gas as possible. Yeah.
well, yeah, we're paying for it. The government's paying for it. I mean, they put it into the budget. They don't care. It's not my problem. If it's $5 million a year to heat this place, it's $5 million a year. Put it in the budget. We'll get it from the government. So we go in and we look at this system and we say, okay, we can only put out 2,418,000 BTUs per hour. And we would like to divide this load by 4 boilers. And those 4 boilers will have a turn down capacity of 20 to 1. So essentially, we end up with a building turn down ratio of 80 to 1 because we've got 4 boilers that are capable of doing it at 20 to 1. And the internal control logic on them will cycle them basically on and off and stage them so that you have the equivalent of an accelerator pedal that can go from idle to full speed in very short order if necessary. But its minimum turn down capacity is going to be 20% of its overall capacity. And basically, we ended up with a physical plant that was capable of handling the load with a minimum of operating boilers. And the boiler control logic would basically change lead and lag boiler based on runtime every 24 hours. So you didn't have one boiler that was always the lead that would eventually burn itself out. You were spreading the load across all 4 boilers and gave them a substantial turn down capacity, which is going to reduce their energy consumption. They were a modulating condensing boiler, so we eliminated the stack action. These are actually vented horizontally through the walls of the mechanical room. We're able to completely block off all of the combustion air because basically we had combustion air that was piped separately to each one of these boilers. So we knocked the snot out of their fuel bills. I think we reduced our gas consumption by like 50%. So we've determined what the load is. We divided that by 4. That told us what we needed in the way of a boiler. Basically, we had 605,000 BTUs roughly divided by 0.81. The 0.81 is a combination of thermal efficiency of 90%, so you see the 0.9, and the altitudinal duration factor of 0.9, because it's not 4% per thousand foot, it's 2% per thousand foot for a sealed combustion condensing boiler. And so we take that 604,500 and divide by the combined combustion efficiency and duration factor of 0.81, and it tells us that we need an input capacity of 672,000 BTUs per hour divided by 4. Okay, so the domestic hot water load can and does often exceed the space heating demand. I'd mentioned that earlier. And in a typical apartment complex setting, that's true. Your domestic hot water demand is going to occur typically between 6 and 7 o'clock in the morning, and everybody and their mother is going to be in the shower at the same time, and they all want hot water. And if they run out of hot water, they're going to be on the phone to management, and management's not going to be happy with you or the people that are running a physical plant. So typically the engineers will say, okay, well, domestic hot water is the biggest load, let's size to that. And when the boiler is doing space heating, again, you end up in that situation where they're grossly oversized. And the worst thing that you can do to any physical plant is to oversize it because it causes short cycling. The best thing that you can do to a physical plant is to undersize it, provided that you're not going to create any conditions of discomfort so that it runs all the time as needed. And with these modulating boilers, they only run at whatever capacity is necessary to maintain the supply water temperature that we dictated through an outdoor reset curve. But remember, I said that the domestic hot water heating system had been replaced, which it had. And in the course of being on site, we see the maintenance guys coming through all the time and punching buttons on the machine to reset it. And it's like, is there a problem? Yeah, we got to do this every day. Well, why? Well, we don't know. And we can't find anybody to work on it, but you got to come back in and punch these resets on these things. And it's like, that's not normal. You guys have got a problem. So we looked into it and found out what the problem was. The appliance had never been serviced and were in dire straits. One of them was completely locked out. The combustion chamber had completely collapsed to the point where they couldn't get any flue gases to go through it at all. And it was leaking water. I mean, with a condensing appliance, you normally see water leaking out of there, except when it's off, it's not supposed to be leaking water. And these were leaking water all the time. So we talked to management and said, hey, look, we would recommend that you allow us to put in some reverse indirects and tie them into these boilers and provide you with domestic hot water. And of course, their engineer got involved and said, well, you need this much BTUs per hour. And it's like, well, if it were an apartment complex, that would be true. But this is a HUD subsidized senior housing project. These people don't get up and hammer the showers at 6 or 7 o'clock in the morning. Some of them don't take but a shower a week, and it's usually after they wake up at 11 o'clock in the morning. So the demand profile is completely different from this building than it would be for a regular apartment complex where the people were working. And showed them that essentially we had the more fire capacity available with the 4 space heating boilers that were derated at 604,000 BTUs per hour than what they had. They had 3 water heaters, and I think they were 199,000 BTUs per hour input each. And again, 0.81 for the net output. So they were getting basically 160,000 times 3. So about 450,000 BTUs per hour out. And when the water heaters were new, they had no problem. So we said, all right, if you allow us to put in this reverse indirect water heater and tie it to the space heating boilers, we can exceed what you've got, satisfy the domestic hot water heating, and you have a very thermally efficient system. Did I hear a question? All right, moving on. So we sized the boilers to the largest connected load, which in this particular case, the domestic hot water load was less than the space heating, but in a lot of cases, if it's a regular apartment complex, it's going to be more than the space heating system. You have to recognize the potential for picking up additional work, which we did in this case. They were reluctant to spend additional money on the reverse indirects that we were going to be setting to tie into the boilers for domestic hot water production until their engineering department got involved and said, 2 of the 3 units that we have are dead and need to be replaced, and it's going to cost us about $10,000 each to replace them. Well, that's basically the same cost that it would have cost for us to put in a reverse indirect. So they said, okay, yes,
Can you explain a reverse indirect?
sure. Typical domestic hot water sidearm heater has a tank with a coil in the bottom of it. You run the boiler water through that coil and it transfers its heat to the potable water that's in the shell of the tank. A reverse indirect is a large storage tank that has a very large coil in it, a very large surface area that you run boiler water through the tank and you run the potable water through the coil. Hence the name reverse indirect. A large surface area. These things are 98% efficient in transferring the heat, whereas uh, pick a brand, Lochinvar, whatever, any one of the regular ones that have got just the coil down in the bottom are limited to about 200,000 BTUs per hour. And that's under ideal conditions. And those ideal conditions are that you've got 180 to 200 degree Fahrenheit water working through the coil with 40 degree Fahrenheit water coming into the bottom of the storage tank and 120 degree Fahrenheit water leaving. The potential of hitting that ideal condition are slim to none. So they're really not all that thermally efficient. The regular indirect is not all that thermally efficient, but the reverse indirect with all that surface area of that coil is basically 98% efficient at transferring heat from the boiler water to the potable water. And these boilers that we're using are low mass. So it takes them a heartbeat to get the water temp up to the max production temperature. They prioritize domestic hot water calls over space heating calls, so you don't end up with a diluted water temperature coming from the heat source going into the reverse indirect. It hammers it with 180 degrees Fahrenheit in a heartbeat. No complaints of shortages of hot water. That answer
Thank
your
you.
question, Tom? Sure.
Good.
All right, so we configured the system layout and designed it such that it can accommodate future expansion, domestic hot water in this case. Management was still leery about doing that. until engineering convinced them that there was an issue by showing them all of the complaint tickets that they'd gotten from people that said, yeah, I have a lot of problems trying to get hot water in the far end of the building. And in a lot of cases, the problems associated with domestic hot water are really not source issues, they're distribution system issues. And I'd mentioned to Tom, I've got another program that if I can track it down and find it, it's on one of my older laptops that I did for Calefi, where we installed these thermal balancing valves on the circulation return system, balance the system out thermodynamically, automatically. And basically, all of the complaints about shortages of hot water went away. Their water consumption dropped by 30%. Their energy consumption dropped by 20% because people on the far end of the system weren't turning the shower on and then walking out and getting a cup of coffee and having toast and waiting for the hot water to get to their apartment before they jump in. So look at these systems as a whole. Talk to the engineers on site, ask them questions, and get as much information as you can because it's going to come back to you. If you say, okay, we're going to put in the boiler, we're going to do the domestic hot water heating system through whatever system you want, flat plate heat exchangers or storage tanks or indirects or reverse indirects. When they start having problems with the domestic hot water heating system, guess who owns it? You do. Even though it's not your problem, it's connected to the system that you installed, therefore it's your problem. So ask as many questions as you can, find out what's going on. So we have to accommodate the system needs during the retrofit consideration. Ideally, if you can schedule this boiler replacement to happen during the summer months, it's non-issue. They don't need any space heating systems. But if the boiler is also doing domestic hot water, then you're going to have to accommodate that need. And in a lot of cases, it's tough to do. We had portable hot water generators that we would drag out into the field and pipe temporarily to keep the domestic hot water heating system available, but they don't have the capacity. They don't have the storage. They don't have the BTU power input that the old system had. So you're going to find yourself in situations where you've got to get the residents to help you work their way through this problem until you can get the physical plant back online again. This is the floor plan of what we had done. This dark line is essentially the housekeeping pad that those two Ajax boilers are on. And we put in Patterson Kelly modulating boilers and basically put in them in such a manner that we were able to actually get both boilers, both sets of boilers, four boilers total, installed and pipe them as a secondary to the primary that was going through the building. It worked out quite well. It's clean, it's accessible. You can access the heat exchangers, which require maintenance on a regular basis without blocking access from the other side. All the controls are readily accessible. You just think ahead and try to design this so that it's accommodated in the way of service. There's the old boilers. You can see both of them there. And this was what we had actually put down in the way of a floor plan. And we actually ended up chopping and dropping those. Yes, that is asbestos on the stacks. We had to have an abatement contractor come in and abate all of the asbestos that was on the boiler stacks, which oddly enough kind of came back to bite us later because they had had another asbestos abatement contractor that was working on the piping distribution system within the building that left a whole shipping container of asbestos out in the parking lot. And they thought it was ours, and it wasn't. So make sure that your abatement contractor does a good job of documenting what he's doing and how he's getting rid of his material so that somebody else's screw up doesn't come back and bite you.
Hey, Mark, you know what else would help while you got your temporary domestic hot water boilers in?
Sure.
Is you go online, you can find there's like health benefits to cold showers versus hot showers, and you hang those on the community bulletin boards a couple months before you even get started. And then you get a percentage of the people who learn to take cold showers. And
Yeah. Yeah, I don't know. These people are HUD
every little
subsidized.
bit
It's going to
helps.
be pretty tough.
Every little bit helps.
Yeah, it does. So is the production of the domestic hot water heating system dependent upon the hydronic system as its heat source? If it is, then you're going to have to accommodate that. And what are the demand profiles for the domestic hot water heating system? If this is a senior retirement center, there is no demand profile. I have physically monitored these things for months and there is no repeat other than when bingo night comes around, they hammer the hot water heating system. They all want to smell nice for their neighbors. But other than that, there is no typical demand profile of peak load between 6 and 8 a.m. and then it drops down to nothing until a bump at lunch. And then back around between 5 and 6 o'clock at night, there's another spike as people are coming home from work and hopping into the showers again. So it depends on the building and what the demand profile is. There are actually, ASHRAE has domestic hot water demand profiles for just about every configuration that you can think of. School dormitories, athletic facilities, apartment complexes with regular working people, senior citizens. They've got the gamut, so you could see what's going on. Can the demand be spread out over a longer time frame? In a lot of situations where we're going to be basically putting in a temporary system that only has half the capacity that the other system is, you're going to have to ask people to do you some favors. And this was a typical letter that we would put out to the residents when we were doing these retrofits and explain to them that we were working on this problem, that they were going to run out of hot water if they all hammered the system at the same time, and ask them basically to spread their use out so that everybody has access to domestic hot water. And believe it or not, people were very, very amenable to this situation, as long as we promised them that when we were done, they were going to be much happier and that the system was going to work better than it had ever worked before. And you don't make claims like that unless you know what you're talking about. So we worked it out and it worked out quite well. So here we are. Where are we at? Demands profile can be spread out over a longer time frame. Yes, in most cases it can. During initial site surveys, talk to the residents, ask them about their comfort and any issues with the domestic hot water heating system. If you ask maintenance, they're going to lie to you. No problem. They're so used to people complaining that they think that's standard operating procedure. Yeah, we always ran out of hot water, but just tell them, wait a minute, it'll be back. When you talk to the residents, note the times that they talk about. Is it the peak demand 6 to 8 a.m.? No, it's all the time. On this end of the building, we never get hot water. That's not a source of supply issue. That's a distribution issue. And you need to mention it to maintenance and management and say, look, we're putting in this new domestic hot water heating system, but you've got issues in your system that need to be addressed. And we're the experts that can do that. But it's going to cost you money. Hire us to come in, take a look, see what you've got. You guys have Moen shower valves out there?
Yes.
Yeah.
A little single lever
Carl
pull out
headquarters
thing?
is here.
Those are the worst cross connection between hot and cold water lines that there is. Moen knows it. At one point in time, Moen was giving cartridges away because of the bad name that they'd gotten in the industry from cross connections between the hot and cold water, which would basically send lukewarm water up the main, anything above that. And if you replace those cartridges, then all of a sudden the cross connection goes away and the problem goes away. So look at the valves. What kind of valves do you have? Do you have Moen single lever cartridge valves? You need new cartridges everywhere. Interview the maintenance people and ask them about any issues that they're aware of and let them know, hey, we're talking to the residents too. Um, are there any issues outside of the mechanical room scope that you want to talk to us about? Any pinholing in your domestic hot water circulation return lines or in your domestic hot water supply lines? Pinholing is not a normal occurrence. It's a common occurrence, but it's not a normal occurrence. Pinholing indicates excess continuous velocities, which on the circulation return systems are quite often a problem where they say, yeah, it's the circulation return pump's not big enough. Let's put a little pump on there. Let's put a bigger pump on there. Let's put an even bigger pump on there. If a little pump did a little good, a bigger pump will do a lot of good. And they end up setting up a scenario where the velocity of the water exceeds 7 foot per second. It's running 24 hours a day, and it creates holes in the pipe, basically erosion, corrosion. The best example of erosion corrosion is the Grand Canyon. And you do not want the Grand Canyon in your piping distribution system. So it's not a problem of undersized pumps. It's a problem of system design and imbalance. And these are potential points for you to go in and take care of these issues. You're the expert. It may be considered plumbing, but basically it's a hydronic system. It's just under a higher pressure. So these were the domestic hot water heaters that they had on site. and they were all broken. They were having to reset them on a regular basis, which is not normal. But they get used to doing this kind of stuff, and that's kind of what it is. I had a job, I think, as a matter of fact, it was in Ohio. It was in Cincinnati. I used to consult a company called AREA, which is the Associated Inns and Restaurant Company of America. And I had their largest hotel was in Cincinnati. And every time they had a convention that had a lot of women, they would send their engineers down to the main circuit breakers for the hotel to spray liquid Freon on the circuit breakers so that they wouldn't trip. I said, what? They said, yeah, well, if we don't, we'll trip. And if we trip, then it's a main pain to replace the fuses and reset the system again. And I explained that to the guy that I was working for. I said, do you know what kind of a hazard you've got going on here? And he looked into it. He says, yeah, anytime there's a convention of women, they bring their own hair dryers. And our hair dryers draw 1,500 watts, whereas the hair dryers that are in the rooms that are a part of the bathrooms only draw 500 watts. So it causes the main breakers to trip. Like, yeah, you got guys down there spraying Freon on them to keep them cool. That's not a normal consideration. And they considered it normal. That's standard operating procedure. Yep, we got a convention of women. Okay, George, you're in the mechanic room tomorrow with the Freon spraying the breakers down.
So you can get
Not,
300 amps out of a 200 amp breaker. Yeah.
yeah, you bet. You keep it cool enough, you can do it. So
I
also
say,
ask management to provide you with copies of thermal energy utility bills. Get real-time data as it pertains to the occupants for reverse analysis, and look at those and compare them to some of the other properties that you've worked on to see how far out left field their physical plant is. And you'll know primarily by looking at the boiler and how it's set up and how it's being operated and how much draft is being run through the breaching systems on those boilers as to whether or not they're efficient or not. And in most cases are not, because nobody knows what they're doing. And whoever, if anybody, is doing any kind of maintenance on them, um, theirs is not to wonder why. Theirs is to keep it hot or die. They don't care. They're not paying the bills. All right, so you determine route, manner, and method of replacement while maintaining service. These are all key sales points for management because they don't want the system shut down and start receiving complaints and deal with complaints on a daily basis. You develop a basic floor plan to make sure that you can put 5 pounds of sugar into a 2 pound bag and not tear the seams, and also have it accessible and serviceable for future needs. We get called into boiler rooms all the time where this is not taken into consideration, and it's like, oh Lord, we're going to have to pull that boiler in order to pull the heat exchanger out of this boiler. It'd be cheaper and better off just to replace both boilers, even though you don't need it. Think ahead, plan these things out. These are all sales features that you can point out to the people that are making the decisions to spend the money. So in this particular case, access for B1 is right here. B2 is right next to it, but you can pull the heat exchanger out of here and you can get in and service that heat exchanger. These are Giannoni heat exchangers. And essentially, you can service the heat exchanger without running into any blockage in front of it. Think ahead. Check regulation compliance and system compatibility. You've got a federally subsidized building here, and they're going to be using probably state and federal funds to replace these boilers with. See if there's any requirements from either the state level or possibly even the federal level if HUD's involved as it pertains to these. Um, Over the last few years, I'm glad I got out when I did, because in talking to some of my former work associates, I'm finding out that a lot of city governments have come up with their own strict standards of electrification. And they look at these buildings and go, no, we want all electric in here, heat pumps for the walls or heat pump boilers or whatever. And it's like, have you looked at your electrical lines to see if they can handle it? Have you checked with your utility? In a lot of cases, they haven't. And when they do, they find out that they can't. So make sure that you've got all of your ducks in a row and don't show up to the game and they go, oh, you can't put gas in, you got to put in electric. Well, the building's not compatible, so let's talk. Check for environmental concerns. Are there any ACMs? Are there any PCBs, any mercury on site? Take that all into consideration, because when you own it, you're going to own everything. You touched it last, therefore you are responsible for everything that's in that building. Include all subcontractors in your walkthrough, your abatement contractors, your equipment handlers, your variable frequency drives, which we put onto these buildings, lighting, etc. VFDs for these pumps is something that a lot of people overlook. Number one, the demand, peak demand is only going to be for 2% of the time, 2% of the heating season here in Colorado. I'm not sure what it would be over in Ohio. It's probably that or somewhat less. But in any case, that means the physical plant's grossly oversized for 98% of the time. And anything that you can do to turn these pumps down when demand is minimal is going to save electricity, and it's also going to save kilowatt demand.
What's
There's a
the what's the ACM?
asbestos containing materials.
Oh,
The variable frequency drives can be applied to probably 90% of the pump motors that are out there. And you essentially use a pressure differential control and convert that pressure to feet of head and maintain the required feet of head in that system. And the pump doesn't care what the GPM is. It's looking at the feet of head saying, I'm going to maintain this. And as valves open up, the head drops, so the RPMs increase to maintain that head. And when you get to design condition where everybody's zone valve is open, then it's doing the same thing. It's keeping that pump running, maintaining only the head necessary to create the flow, which, if it has been properly sized, it'll work out quite well. You have these non-electric thermostatic control valves that are in all of the rooms, which essentially is a modulating type of control. You've got basically, excuse me, the dog wants to get in here. He's learned how to open the door, which lets the cat out. Basically, you end up with a fully modulating system. You've got modulating boilers, you've got a modulating pump, and you've got modulating control valves so that the system reacts to the actual real-time scenarios. Remember the picture of the building, this one right here, that's the north-facing side of the building. The south-facing side is just as large, but it has sunshine coming into it, which means that even if it were design condition, if it's sunny outside, the south side isn't going to require as much heat as the north side is. So by having these modulating controls in there that can see real-time demand, you essentially have the equivalent of an accelerator on their heating system instead of an on-off switch. And the boilers can modulate, the pumps can modulate, the flow will modulate at the point of use, and you end up with a living, breathing system that's going to be able to save a significant amount of energy.
What were they doing for cooling in that building?
The only cooling that was occurring in that building was basically in the hallways. So they had evaporative coolers on the top floor of the building on the outside, and then shafts that ran down all the way through the building, and basically were dumping cool, humidified air, which we can do here in Colorado. I don't think you'd want to try this in Ohio, but
Yeah,
evaporative cooling is quite
you know,
effective in providing cooling in the building. And the windows were also operable. So if the residents wanted to, they could open their windows at night and provide free air cooling. So exchange photographs and field observation notes with all of your subcontractor teams that you've brought in. They may have seen something that will affect you, and you may have seen something that will affect them. They're going to be working for you. So it's important that everybody gets all of their bases covered so that nobody is surprised by anything. And then it becomes time for the lawyers to come out, which gets expensive for everybody. Plan your work and then work your plan. CPM is critical path method scheduling. You've got to get the abatement contractor in first. When he's done, he has to call for an air test. When he's done with his air test and the building is cleared, then you can start moving in with your equipment handlers. We have a company here in Colorado called Boiler Busters, and they're just the best people in the world. We tell them we spray paint on the pipe from here to here, make everything disappear. And they do. They come in and they use torches. In the particular case of these boilers, they cut them apart with torches. They cut the tubes out. They cut the tube sheets out. They make everything disappear. If it's a cast iron boiler, they'll break it up into small sections that are manageable and carry it out. And when they're done carrying it out, then they carry everything in for us. And we just make a mark on the floor and say, put the boiler here, 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 and here. And they do. It saves our crews from having to handle equipment. It saves them being exposed to the potential of bodily injury. from moving the equipment. These guys are pros. They know what they're doing. So coordination meetings with all of your critical subs and building management. Make sure that if you have to use a crane, that you've got the necessary clearances to get it there, that they've got all the permits necessary from the city to block streets if they have to, whatever it takes to be able to get the job done, and make sure that you've got everything planned for, and then obtain the necessary permits, state, city, and federal when required. Coordinate critical components and schedule their delivery in a timely manner. You don't want a bunch of equipment laying around that's not going to be installed for 3 months, but you've got to make sure that when you need it, that you can get it and that you're not sitting there going, where's the boilers? Can't put them in if we don't have them. Coordinate your manpower and schedule accordingly. We had 6 installation crews with advanced hydronics, and they were busy every day of the week. And we were booked, I think when I left, we were booked 6 months out. I had lunch with the owner the other day. He said he's booked a year out now. Perform progressive billings to stay ahead of your cash flow. Don't wait until the end of the job and turn in one big bill. Make sure that that is a part of your contract with whomever you're working for, whether it's a state agency, the ownership, or whoever it happens to be. Let them know that when we get done with rough, we're going to bill you for 33% of the material. When we get our rough inspection, we're going to bill you for an additional 33% of the job. And when we're completely done, we're going to bill you for the balance plus any change orders. That way there's no surprises. They've got money set aside. They can pay you in a timely manner. You can pay your suppliers and your subcontractors in a timely manner, and everybody goes away happy. Request and receive all necessary inspections before your final billing. That way they don't have any leg to stand on to say, well, we don't think you're done. Yes, I am. Here's the inspector's sign off. It meets code, it exceeds code. It's time to pay the bill. Perform full startup and commissioning prior to submitting your final bill, and make sure that you document that. I know in Colorado, they actually wanted a commissioning agent to come in, which was a part of our subcontracting. I wanted my guys standing there on site whenever this was happening, and they kind of liked that too, because a lot of commissioning agents don't know how to override these controls on these boilers to send them to full fire or to send them to minimum fire. And so having a qualified technician on site, the guy that set the boilers up and started them up in the first place, is pretty important for the commissioning. But basically, you have an anchor that says at day one, we were here. And if you don't do service on these things, it's going to show, and have a service agreement with them and say, these have to be worked on. Your old one didn't, and look what happened to it. It ended up burning itself out. So service is required. Build it into your budget, plan on it, and we'll be here to handle it. So here's the actual installation. You can see the boiler breaching back here of the existing boiler that was left online, and then the placement of these 2 boilers and the secondary piping that was installed. Each boiler had its own individual pump. It was a 2-man job for the actual boiler installation itself. There's another side view of the Patterson Kellys. It's a modulating condensing appliance. Expansion tanks were in good shape. Those are ASME tanks. Here's the domestic hot water circulation return pump. Remember when I said a little pump does a little good, a lot of pump will do a lot of good? This building was springing leaks in all of the circulation returns about an inch after every elbow. And I said, well, it's easy to diagnose. The next time they fail, cut it out, split it, open it up, and look at it. And remember that horses always walk upstream. You'll have a U-shaped pattern of erosion from the water flowing in this direction because horses walk upstream. So it looks like a horseshoe print. And that's not a normal consideration. The plumber always says, yeah, they don't make them like they used to. Yeah, you're right. They actually make them better than they used to. The problem is, number one, your plumbers didn't ream their pipes. And number two, the pump is grossly oversized. So it's pushing water through these pipes at greater than 7 foot per second, which eats the pipes. There we are. moving through, getting these boilers in, pressure tested, getting them ready to fill and fire, rock and roll. Once we've got these boilers online, and then we can chop and drop that other boiler. And there's the domestic hot water heating systems with the red lights that were always on, indicating the need for reset. This one was completely dead. The flue gas passageway was completely collapsed and blocked, and was leaking water continuously out of the condensate drain. So look for those as potentials. Um, you may not see it during your initial walkthrough, but keep an eye out for it and talk to the residents as well as the maintenance guys and listen fairly to both sides and see if you can figure out what's going on. So there was the completed installation, nice and clean, tight. It was kind of 5 pounds of sugar in a 2-pound bag, but it was necessary. It was serviceable. It was accessible. There was our frequency drives. Used a variable frequency drive, and these are a pressure transducer that essentially converts PSI to feet of head and gives a 0 to 10 volt signal to the variable frequency drives so that as valves start closing down and the pressure increases, then the RPMs on the pump decreases, thereby reducing kilowatt hours and kilowatt demand of consumption and lessening the amount of wear and tear on the system. Basically making the pumps modulating as well as modulating boilers as well as modulating heat controls. Oh yeah, make sure that you let maintenance and management know that instead of seeing steam coming off of the top of the building like they used to with the old boilers, that you're going to see steam coming out of the side of the building. And in some cases, it may be necessary to block windows. I mean, in this particular case, it wasn't because this is a stairwell that was interior and there were no operable windows going into that stairwell. So we didn't have to worry about any of the potential of condensation from these boiler vents being drawn back into the space. But I have seen situations where we had to block windows due to the vent termination and set them up in such a manner that you don't cause problems for yourself. Let them know in your initial walkthrough. Take pictures like this to them and say, expect to see this on a cold day. This is normal. Any questions? Hey, look, Tom, you've grown up. Area 51 or SES.
Got it.
Any questions? Doesn't have to necessarily be on this particular installation. If you got domestic hot water questions, whatever, I'm here.
What about the condensate, somebody calling the fire department because it looks like smoke?
I've never had that problem.
That,
Usually the biggest complaint that you might get will be if somebody gets a little whiff of it on their porch because they're not used to smelling the byproducts of combustion. There are aldehydes in the natural gas that were part of the compounds that they put in to make the natural gas stink. And they will burn your eyes. They'll sting a little bit, but it's not deadly. The parts per million are very, very low as far as carbon monoxide is concerned. It's just they're not used to it. So again, it's a matter of education of the engineering department to let them know that, hey, if somebody complains about this, let them know, number one, it's not going to kill them, but they should avoid breathing it if they possibly can, and to expect it because this is a new system.
It's not gonna kill them if proper maintenance is being done on the boilers.
True. Yeah, and maintenance is key. Unfortunately, a lot of these companies will switch hands. And when they switch hands, the new company comes in and goes, we're going to show you how to make money. And their idea of making money is not spending money on things that are critical, like maintenance on the boilers. Are they working okay? Yeah, they're working okay. Well, then don't maintain it. No, you got to maintain these things. If you don't maintain them, they're like a redheaded stepchild. They will go away.
So when you said the boilers was twice oversized, can that be repiped only on one boiler?
Yeah, they could have actually. And again, it's a matter of knowledge. The maintenance guy doesn't know. He doesn't know that he could actually operate on one boiler and switch them daily. Just one boiler would have been more than adequate to take care of the space heating needs for this building, even at design condition. and design condition only occurs for 2% of the time, but his job is to keep it hot, not to wonder why. He doesn't care about the utility bills. What he doesn't want is his phone ringing from anybody saying, it's not warm enough in here. So the best way to do that is to keep both boilers lit and running. And if one goes down, then the other one's there to pick it up. But,
So Mark,
if,
sorry to interrupt. That's what I was thinking about originally when you brought that up. With losing the domestic load, you could basically run lead lag off those two boilers then, and
yes,
it wouldn't have that capacity.
yes. And, the turn down on these boilers where it would go to low burn, which is 1/3 of the capacity of the boiler, is really not efficient. I mean, if it were a 1-story building, it would probably be okay. But with it being 13 stories tall, having significant stack action, having 5 pounds of weight on the barometric damper, when it goes to 1/3 burn, the amount of dilution air that's being drawn to the combustion process basically turns the efficiency of the boiler down to about 40%. So they're running on a 40% efficient boiler for 98% of the time, which is not good. But that's the nature of the beast. It's been that way, and you're going to run into these boilers still. They're still making them this way. It's like it doesn't make any sense. And they're like, well, that's what the market demands. I mean, you'd be amazed at how many decisions are made by the sales department and not the engineering department in a lot of these boiler designs and configurations. Well, that's easy for me to sell, but it's not the most efficient. I don't care.
It's
My
the
job is
cheap.
not to wonder why. I want to sell boilers.
Did you guys during the sales process calc out the actual savings and efficiency? I know you said you saved around 50% on their gas bill. Did you give them those numbers too?
Yeah,
The numbers we gave them were 30%. If
30%.
you go from 80% efficient boiler to a 95% efficient boiler, you would think theoretically it should only be a 15% reduction in fuel consumption. It's not, it's 2 times that. So just the
Well, yeah,
base,
because we're heating all the flue gas.
right. So the base difference in seasonal operating cost of going from an 80% to a 95% efficient boiler is 30%. That's the minimum that we have seen. So that's what we used in our economic analysis of making them do this, or giving them incentive to do this, is a 30% reduction in fuel consumption, which would show a return on the investment in about 7 years. Very reasonable. What they actually saw was a 50% reduction in consumption, but they didn't call us up and thank us. They took the money and run. We had a conversion. Downtown Denver has the oldest continuous operating steam district heating system in the world. And in high-rise buildings, it's kind of a godsend. It's great. You got 100 psi steam coming into your building. You've got converters that convert it from steam to hot water, and you've got the conventional hot water distribution system, fan coils, baseboard, radiators, whatever in the building. But the cost per therm for that steam is about 3 times the cost per therm for natural gas, because you've got continuous losses from the mains. You've got a huge maintenance factor in the steam driving force itself, the boiler room. It's just a very expensive process, but most of the people that get stuck with those buildings don't know that there's an alternative. We got called into one down in Denver. I think it was 12 stories tall. It was built in the 70s. It was a part of that rush to HUD, and it was on steam. And the steam system had not been properly maintained. It was in terrible shape. The whole heating system was in terrible shape. And we went and looked at it and said, yeah, there's natural gas out in the street. We could convert this to natural gas in a heartbeat and reduce your cost of operation by 2/3. Just the basic cost per therm. We're not going to make any changes in the loads. We're just changing the source. We're going from $1.50 a therm down to 50 cents a therm for the natural gas. And they said, hey, that's a pretty good idea. So we did it. And it was, I think, a $1.2 million job, paid for itself in 1 year in fuel savings. I mean, we didn't tell them that. That's just what the numbers worked out to be. They were happy. They called us back and thanked us.
Mhm.
Mark, on the Patterson Kelly boilers, you're probably looking at 13 stories, you're probably looking at 51, 54 feet ahead, something like that, static.
Yeah.
So those were directly coupled. There was no heat exchanger between that and
No,
okay.
no, and we had room on our relief valves to handle it. I think they're 125-pound relief valves.
We had a building identical to the one you're showing. It had some Viessmann boilers on it, but were not coupled. I'm sorry, that had a plate frame between it and it's just
Very
complicated.
common. Yeah,
Yeah.
the engineers, when the engineer chooses an inexpensive boiler that is not ASME rated, then he has to have a heat exchanger to handle it because it's only rated for 30 psi. So the way around that is to have the plate frame heat exchanger, have the boilers running at less than 30 psi, and then your system can run at 200, 300, whatever it needs, which, by the way, is a half pound per vertical foot plus 5 psi at the top of the system to physically and manually purge air out. A lot of people don't understand that as such a simple concept of how many pounds of pressure do I need to fill a system? Well, it's a half pound per VS per vertical foot of system elevation plus 5 psi. And in a lot of cases, they'll just turn it up. You know, it goes through the turn it up syndrome. They're cold, turn it up. Well, the complaints went away, so it worked. But yeah, that's typical engineering scenario is I can buy these 30 psi boilers for really cheap, and plate and frame heat exchangers are really not all that expensive. So we'll do this and it'll meet code. When in reality, they're not
That
looking
was
at the labor factor.
swamp coolers. That building had swamp coolers, Tom. Did it?
Yep.
Yeah. All right,
Oh,
that
your
looked
building had swamp coolers.
Identical to the one he showed
Yeah,
us.
here in Ohio.
Yeah.
I saw a lot of that. As we would go through these boiler rooms, it's like, gee, this looks really similar to the one that we worked on before. I think there was a set of standard plans that all of these HUD contractors were using that was like 10 specification. Yeah, put in the boilers and do the domestic hot water through these side arms and be done. It's like, okay, that's not real efficient. But back in 1970, efficiency wasn't really paramount on anybody's mind. It was getting these buildings filled with people that they could take half of their income for rent and call them sheltered.
Cleveland has uh, steam also.
Do they?
Yeah,
Bagman still has it.
Cleveland's got steam and chilled water.
Chicago's got chilled water.
Denver's got chilled water too. XL Energy has a chilled water plant down in Lodo. It's 3-story tall building. The cooling tower's on top, and they have separate chilled water circuit that runs through lower downtown Denver that quite a few of the high rises are on. Tom, did you get a chance to see the 16th Street Mall when you were in Denver?
No.
It's been a long process in building and stuff, but basically they eliminated automobiles and they only let buses and humans and bicycles go up and down this mall. And they had contacted me at one point in time and said that they wanted to put snow melt in because they had basically converted everything to kind of a brick type of tile in this whole mall. And whenever they used their snow plows, it would catch the bricks and tear the bricks up. So there was continuous maintenance on these inlaid bricks on the 16th Street Mall. And they decided that they wanted to put a snow melt system. Excellent idea. Down the 16th Street Mall so that they wouldn't have to run plows on it. And I said, well, here you go. At the east end of your mall, you have a cooling plant that is rejecting heat into the atmosphere.
duh.
They could provide you with free heat to run through your snow melt system and just keep it in idle all the time. And it's going to work much better. I don't know how many of you guys work on snow melt systems, but a snow melt system works proactively much better than it works reactively. So if you know a storm's coming, start warming the oven up. And when the snow hits, it will melt immediately instead of it starts snowing and the system goes, oh, hey, we need the boilers. Well, the slab's cold, the boiler's cold, the fluid's cold. It takes a while for all of that to gain its momentum and get that surface up to the melt point. And by that time, you've got accumulations occurring, which nobody wants to see. I paid for a snow melt system. Why am I seeing snow in my driveway? So they could have had the potential of being able to do that, but Xcel Energy said no. So we don't want to sell them that. The same thing happened with Mile High Stadium. Believe it or not, the football field has a turf conditioning hydronic heating system below the turf. That's the reason that that grass is so green in December, is because they're heating the root zone.
Brown
There was
Stadium,
a, pardon?
the Brown Stadium has heating
Yeah,
on the
yeah,
turf.
a lot of the NFL fields have gone to that. But probably 2 blocks away from Mile High Stadium is Xcel Energy's natural gas powered steam turbine that provides not only electricity through steam generation, but also steam to a lot of the Capitol complex. And they have to reject the heat from that steam on the turbine in order to keep the turbines operating efficiently. And guess how they do it? With cooling towers. And it's like, they got a company that would pay to put a line between your power plant and this stadium and would pay a discounted price for the energy that's necessary to maintain the turf within the stadium itself. And they said no. I don't understand their logic, but they said no. So it didn't happen. I mean, I'm a big fan of recycle and reuse. Anywhere that it is possible, I would recommend that you do it. I've got a drain waste heat recovery system on my house up in the mountains that Tom has seen that essentially recovers 50% of the exiting energy that's headed for the septic system and uses it to preheat my domestic hot water. If I were to put a solar system in, it would cost probably 10 times as much money as I paid for that heat exchanger to do the same thing, to deliver a 50% reduction in energy consumption for domestic hot water production. It's here. It's a technology that's available. It's actually mandatory in Quebec, Canada. Any new construction has to have a drain waste heat exchanger installed as a part of the plumbing. Those people get it. But any potential that I see of something like that, of being able to recover waste heat, it needs to be taken advantage of. And there's not enough people doing it.
Mark, we did an ice rink back in the eighties, and in the wintertime, we probably make up 3,500 gallons a day for cooling water.
Mhm.
And I can't remember how many tons it was, a couple of hundred easily. So we were talking about the chiller system there. I can't imagine the evaporation that takes place, how much water is being spent. Or it can't be air cooled, can it?
No, no, they were definitely cooling towers. They were using evaporation to be able to enhance the cooling capacity of the cooling towers themselves. Speaking of cooling towers, water quality actually was chairman of an ASSE committee that put together the hydronic water quality standards for closed loop hydronic heating systems. And we kind of, during one of our meetings, delved off into a branch that we didn't realize that we were going to be talking about, and that is cooling towers. And you guys are probably familiar with this, have to maintain a certain level of concentration of chemicals within the water itself before they become scaling. And essentially, you bleed water off to dilute the water that's in the cooling tower to maintain the required level of concentration of cycles of concentration from evaporating water. What do they do with that bleed water? They just send it to the sanitary sewer. I mean, that's that steam system that we worked on down in Denver. Denver has a code requirement that any fluid that enters the sanitary sewer has to be cooled down to at least 120 degrees before it can be discharged. Okay, so the traps that they had that they used for billing the amount of steam was based on the condensate that went through the trap. Well, before they could discharge that condensate into the sanitary sewer, they had to chill it down with potable water. Seriously? You've got a domestic hot water heating system sitting here that could take that condensate, which is free. You already paid for it once. You paid for the energy that basically you took out of it, and use that to preheat your domestic hot water heating system and not have to pay for any potable water to cool it down before you discharge it into the sanitary sewer. And there are so many opportunities like that out there that people just look at and they go, well, that's the way we've always done it. Well, it's time to change. It's time to change your way of thinking. If you were to
Building
put,
out all the data centers, and you can imagine, they're gonna have to pay somebody to plow the parking lot when they're gonna make nothing but heat. There's no reason for it.
if I were to design a cooling system for a data cooling center, and I understand that all of the chipsets on these things are hydronically cooled. They've actually got fluid passageways going through the chipsets. That's how they're extracting the heat to keep the little diodes from popping on these machines. I would go with a ground source heat pump system. I would tie into Mother Earth, which is always nice and cold. There's always a movement of water going through these fields in most cases. In certain cases, you get into a static condition. But then I would also put in snow melt in the driveway so that if you ever did get into a situation where you exceeded the capacity of heat rejection or absorption of that field, that you could then use the slab at night to radiate that heat into outer space. Um, there's a condition called night sky re-radiation that has more influence on human comfort and temperature of demand in humans on the face of Earth than people realize. It's minus 327 degrees Fahrenheit outside of our atmosphere. Heat flows from hot to cold continuously. And so at night, if you've got a saturated field, loop field, then you circulate the water through the driveway and it radiates that heat up into outer space. They actually have IKEA here in Denver. And the IKEA is heated with ground source heat pump. They're on cooling demand for 95% of the time, heating demand only 5% of the time because internal lighting gains, body gains, all of the internal gains basically take care of their need for heat. So they're really more in a cooling mode than they are a heating mode for the majority of the time. But if the loop field gets saturated with heat, they've got a truck ramp in the back of the building that's snow melted that they circulate the fluid through to reject that heat and cool the loop field down. So this is not theoretical. This is actually being done. And it's gotten to the point now where the people in shipping and receiving will place a call to management and say, hey, you think you could melt the snow in the driveway for us? Flip a switch and melt all the snow so that the trucks can get in and out, sliding down the ramp. So yeah, if I were to do a data center, it would be hydronics, absolutely. There would be zero evaporation occurring whatsoever. I'd use the earth as a heat sink. And if that heat sink got too hot, then I would reject the heat with a black body tar asphalt configured snow melt system that would basically radiate the heat up to outer space and cool the system down naturally. That's why I don't want to offend anybody in case you're an engineer, but I don't get along with engineers real well because they don't have any common sense. If they do, they're not applying it.
We're all engineers. You just don't have
We are.
degrees.
True. We don't carry a license. When you get the engineers coming to you with questions and problems, you know you finally hit your goal. Any other questions?
I think you and me, probably others in this room have been blacklisted from some jobs because of that too.
Oh, absolutely. And it's funny because I just shrug it off and it's like, next.
Mark,
Yes, sir.
was gonna say thanks for jumping in and taking care of this tonight. Really appreciate it, and
You're welcome.
I'm sure the guys got a lot out of it, so.
Well, good. And if you guys have any other questions pertaining to this, send them to Tom. Tom will send them to me. I'll answer them and get them back to you. I don't like to leave any questions unanswered.
Thank you, sir. Thanks, Mark.
You're welcome. We'll talk to you guys later. Have a good evening.